All right, guys. So this video is going to focus on Bronsted and Lowry theory of acid-base chemistry. We've spent a lot of time on Arrhenius' theory, but overall, we want to visit another theory that kind of expands or grows. Arrhenius was very restrictive in that you had to have an H to be an acid, you had to have, or a hydronium ion, you had to have hydroxide or a hydroxide ion to be a base. And obviously, we don't necessarily see that as true for all acid-base behavior in our world. So Bronsted and Lowry, they were actually two chemists that worked separately from each other. In 1923, they actually published right around the same time and came to the same conclusions. And their goal of their acid-base chemistry theory was to overcome the limitations of solution acid-base chemistry. So what if you're not necessarily in solution? Or what if you see a behavior that's not hydronium or hydroxide? So their work was independent, yet they came to the same conclusions. Johannes or Johann Bronsted, if I get the name pronunciation here right, was from Denmark, and Thomas or Martin Lowry was from England. And these two chemists both, again, came to the same conclusions around the same times. Their lifespans are very, very similar as you look at years there. These guys were helpful to us in that they took the ideas of Arrhenius and found more options, I guess is the best way to say it. So when they looked at their definition of an acid, their definition made acid a proton donor. And of course, that's very similar to Arrhenius in that it had to give off an H+. So that's not really anything new to us. Same idea that we already had from Arrhenius. But where they expanded on his theory was they looked at a base as a proton acceptor. So you basically have an H going from one to the other. So the base has to have a lone pair of electrons, as you see there in the picture. NH3 is a good example, and you got to have a partial negative charge. We talked about water, how it absorbs the proton to make the hydronium ions with Arrhenius' theory. So we see the same ideas here. You have a lone pair on ammonia, and that lone pair is going to attract the proton, leaving the acid. So what you see on the right side of the picture there is an NH4 plus ion. So from the H plus and the NH3, we are getting the ammonium ion that we see as one of our polyatomic ions. So this is an acid-base behavior. HCl behaves as the acid willing to donate the proton away. Ammonium behaves as the acceptor of the proton and behaves as a base. So we see acid-base chemistry behaving here, and hydroxide's not present. Now, when we think about this theory, it opens up the world to a variety of bases. Now, the acid world is kind of unique. HCl, HNO3, which is our nitric acid, HC2H3O2 is our acetic, sulfuric is H2SO4, and you notice water is in that list because water can donate an H plus away. But ions also can fit this. That's another inclusion that Arrhenius' theory didn't have. You have HSO4 1 minus, H2PO4 1 minus, HPO4 2 minus. You'll notice I'm removing protons, but not all of them at once. Remember, they leave one at a time. And NH4 plus 1 can give away a proton as well, becomes ammonia. So there's the opposite of what we just saw in the prior slide. They're all donors. They all have H's to give. Now, bases, on the other hand, we have proton acceptors. So you have to have a lone pair. So nitrogen and NH3 has that lone pair, as we saw. You notice water's in this list as well. And to the right of the screen there, it's what we call amphoteric. If we think about an amphibian, amphibians are unique in that they can live on land or in water. So the term ampho is a reference to having two behaviors. So for us, behaving as an acid or as a base. So water can donate a proton, but through its two lone pairs on oxygen could also be an acceptor and accept the proton and be a base. OH minus has three lone pairs on oxygen. NO3 1 minus has a lone pair on nitrogen. HSO4, 1 has a lone pair on an oxygen that can attract a proton. That's a little unique behavior. We're not going to look at too much detail of the Lewis structure, but understand that behavior can happen. CN1-, carbon has a lone pair for behavior there. HCN, we've seen that. And then PO4-3-, you have oxygens that have lone pairs that can pull in hydrogens, and that makes the phosphoric acid. Again, another unique one. So sulfate, phosphate, we're not going to look at Lewis structure, but understand they can donate H's, they can accept H's. So that's what we're looking for. So how we refer to this, we introduce a new term called conjugate. A conjugate pair really just means you have a combination of two substances. I'm going to say substances, could be compounds, they could be ions, but you have two substances that differ by one H or one proton. That makes them link up as a conjugate pair. Now, here's the neat part of this. Differing by a proton builds a conjugate pair. So every reaction we're going to look at is going to have two conjugate pairs. On the reactant side, we're going to have something acting as an acid, something acting as a base. On the product side, because it's going to establish an equilibrium, as you notice my two-directional arrow, I'm also going to be able to look at the reverse reaction and have an acid and a base in behavior going in reverse. It so happens that when you look at the conjugate pair, the acid behaving in the forward direction will be a conjugate base behaving in the reverse direction that will align to make a conjugate pair. And we'll look at an example to see that in a better context. Base on the left or reactant side will have a conjugate acid to pair up with on the product side for going in reverse as well. So really what it is if the substance behaves as an acid going forward, it's going to behave as a base going backward. And we will call the backward or reverse direction, we will call it conjugate base or conjugate acid as you see this labeling. So let's jump into example 1. So we have NH3 plus H2O giving us NH4 plus on an OH minus. Water here is, if you look at going from left to right, water has lost an H. There's just hydroxide left. So that donation of a proton makes it the acid. NH3, of course, is using its lone pair to pull that in, so it's behaving as a base. There's your forward direction. Now, if we look at the reverse direction, we find that NH4 plus can give away the proton going backwards, becoming NH3. It's lost it. So you have to think about the reverse direction. NH4 plus is now the donor, so it's a conjugate acid. OH minus is accepting that proton and therefore behaving as the base, becoming H2O. So reverse reaction, you have to reverse your thinking. So in the end, this reaction has two conjugate pairs. The NH3 and the NH4 plus go together, which is your base and conjugate acid. You also have H2O and OH minus, acid with conjugate base. And I color-coded so that you could see that pairing. That's unique. That's different from anything we looked at with all the problems we've been doing for strong acids, weak acids, and strong bases. So Arrhenius' theory wouldn't fit this. Though water does have a hydroxide ion, it doesn't look like the normal acid-base behavior that we saw so far in this course. So that is kind of unique. Now, there's one last thing we want to look at with these Bronsted-Lowry problems. And again, it's all labeling. There's no math. We're going to take the acid and the conjugate acid, and we're going to go to our Ka chart. And in the case of H2O, the Ka value is 1 times 10 to the negative 14th. We're going to see that with our pH equation, our ion product constant for water. And for NH4 plus, we're going to have 5.7 times 10 to the negative 10th. So what we're looking for is which one of those guys is larger. And that larger one is the stronger of the two acids. So 10 to the negative 14th, 10 to the negative 10th. I know that 10 to the negative 10th is a larger value. So therefore, NH4 plus, the larger or stronger the acid, or it wants to dissociate, pull apart, and the reaction will push away from that stronger acid because it's going to ionize better. So it's going to move towards the direction of the weaker acid, strong towards weak. So in this case, this reaction is favoring the conjugate acid moving towards the weaker acid of H2O. So we would say this reaction favors the reverse direction based on that thinking. That's a different concept. And you notice we're ignoring the bases. Our focus is just on the acid and the conjugate acid. Now, some of these reactions, if I look at my next example, I'm not going to go the whole way through it because I want you to practice this through the notes. But if I look at H3O plus and look at it going in reverse, it's going to be a donor. H3O plus becomes H2O going in reverse. So H3O plus is going to act as an acid. And if you look at your Ka chart, you're not going to see it there. We look at H3O plus as the weakest of all the weak. We say that the Ka value for H3O plus is just very, very small. So on the chart of Kas, it would be at the very bottom. So always treat it as the weakest. So whatever the acid is on the left side, it's going to win, and the reaction is going to favor moving towards H3O plus anytime it's present. So that's kind of unique to this, but I do want you to practice reactions 2 and 3. So work through those, and we'll go over those in class. With that, that takes care of Bronsted-Lowry theory. Again, we're only visiting the idea of labeling. So for a test or a quiz, you need to be able to do what we just did with reaction 1 on this slide. So thank you for tuning in, and hopefully this helped clarify Bronsted-Lowry theory to you.